Welcome to Introduction to Programming. My name is Steven.
And my name is Sean.
Over the next 90 minutes, we'll be taking you through this series consisting of 21 different segments that hope to cover the basics of computer programming, which can apply to any and all programming languages you might want to learn. We'll be starting with the simplest question of what is programming, and from there, we will be working our way up as we talk about common features of computer science such as loops and arrays. We'll discuss how to read and write code, debug code that you've written, some strategies to help you plan out your code, and much, much more. The complete list of topics that are going to be covered in this lecture-style video are shown on the screen now. Additionally, there will be timestamps in the description, so feel free to skip around if you are already proficient in some areas of computer science or just want to know about a specific topic we will be covering. Hopefully, by the end of the series, you'll have a basic understanding of what computer science is, along with an armory of useful skills that will help you unravel whichever programming language you decide to learn first. We'll only be covering the major key points that apply to all programming languages, so we'll be shying away from topics such as object-oriented coding and command line navigation, as those are things which are language-specific. Additionally, there will be no software required for you to download in order to follow along with this tutorial, as we won't be writing any code in an IDE to keep things simple and concentrated. This video is meant for those who are interested in computer science and programming but have no idea where to start and have little to no background information on coding. And so if that sounds like you, then strap in as Sean and I work our way through the wacky world of computer science, starting with the biggest question probably on your mind, which is what even is programming?
Well, the dictionary defines it as the process of preparing an instructional program for a device. But that's a really confusing definition. So, in layman's terms, what exactly does that mean? Essentially, it is attempting to get a computer to complete a specific task without making mistakes. Imagine this, for example. You want your less than intelligent friend to build a Lego set, except he has lost the instructions and can only build based on your commands. Remember though, your friend is far from competent, and so if they are not given very specific instructions on how to build the set, there are many mistakes that they could make. If he thinks like a computer, then if there is even one piece that you have not told him specifically where to place and how to place it, the entire Lego set will be ruined, and he will be left to suffer a complete mental breakdown, causing the whole goal of the project to be corrupted. Giving instructions to your friend is very similar to how programmers code. Instead of a less than intelligent friend, you have a less than intelligent computer. And instead of instructions on how to build a Lego set, we are feeding it information on how to complete a program, like a game or a web application. An important thing to note is that computers are actually very dumb. We built them up to be this super sophisticated piece of technology, when in actuality, a computer's main functionality comes from how we manipulate it to serve our needs. Now, programming isn't as simple as giving your friend instructions, since in a programmer's case, the computer doesn't speak the same language as you. The computer only understands machine code, which is a numerical language known as binary that is designed so that the computer can quickly read it and carry out its instructions. Every instruction fed to the computer is converted into a string of ones and zeros, and then interpreted by the computer to carry out a task. Going back to the Lego example, this process would be like if he was not only less than intelligent, but to make matters worse, he could not understand English and only speaks in Mandarin Chinese. In order to speak with him, you have to convert the instructions that you understand in English into the language that your friend understands. This process is essentially what you must do for your computer in order to make it understand the instructions that you give it. The big difference between the two examples, however, is that it is very difficult for people to understand machine code and binary. Directly translating what you want the computer to do into machine code is extremely difficult, in fact almost impossible, and would take a very long time to do it if you could. Each program is composed of millions upon millions of those ones and zeros, so how, exactly, are we supposed to translate our instructions into machine code? This is where programming languages come into play. Programming languages are fundamentally a middleman for translating a program into machine code. These languages are much easier for humans to learn than machine code, and thus are very useful for programmers. Going back to our Lego example, a programming language would sort of be like an interpreter that's able to take the instructions you give them in English and translate them into instructions your non-English speaking friend can understand. This makes programming languages extremely useful and the backbone of any good program. Think of programming languages as not English and not machine code, but somewhere in the middle. There are many different programming languages out there that each have their own unique uses. Languages such as Python and Java act as general-purpose languages that can perform a variety of computational tasks, while Robot-C or HTML or CSS are languages designed for more specific purposes, such as moving a robot or constructing a website. Languages can also vary in how powerful they are. For instance, JavaScript is a scripting language that is designed for smaller tasks, while Java or Python can carry out much more computationally taxing processes. We can measure a programming language's power, or level, by how similar it is to machine code, the series of zeros and ones we talked about earlier. Low-level programming languages, such as assembly or C, are closer to binary than a high-level programming language, such as Java or Python. The basic idea is that the lower the level of your programming language, the more your code will resemble what the machine can interpret as instructions. Aside from the different purposes that each language fulfills, choosing a language typically comes down to a matter of preference, as there are usually many languages that can accomplish similar tasks. Try different languages and decide which one's rules, interface, and level of simplification you like best.
So now that we know what programming is, how do we actually write code? It's not like we can simply type words into a text document and automatically assume that the computer can translate it into machine code, read it, and carry out a task like opening up a browser. And additionally, we can't just write down rubbish in certain programming languages mentioned in the previous segment and expect the computer to understand. So how are we supposed to write code then? Well, the answer is with an IDE. An IDE, which stands for Integrated Development Environment, allows the facilitation of code by a computer. IDEs provide a graphic interface on your computer in which the programmer can easily write, run, and debug code without having to worry about problems with complication or interpretation of the program. Think of an IDE as any other program on your computer, such as a game, a browser, or even the File Explorer, except we'll be using it to write code. IDEs are able to turn your code into machine code and run it through the computer to produce results. In addition to providing a place for programmers to develop their code, IDEs provide some extremely useful tools for programmers to ease the job of writing code, such as built-in error checking, because as we'll talk about later, code doesn't always run correctly, autofilling for frequently used words or phrases, and a project hierarchy, which will help you organize and manipulate the files within your project. Back in the olden days, before IDEs, code used to be written on punch cards and then fed into computers, which would take hours and cause a lot of pain. IDEs nowadays act as sort of a fast track to writing code and make things a whole lot easier for programmers. An example of a specific IDE can be seen on your screen now. In the center you can see the program that is currently being written, and right below it is the console, which can print out useful information for the programmer. This specific IDE is used to write Java code. IDEs are extremely powerful and will be used in almost 100% of your programming projects. So through these IDEs, we are finally able to write and compile code smoothly without worrying about the computer not being able to understand it. The next problem we run into then becomes how do we write this code in the IDE? Because it's not like we can just type random words from a certain programming language and expect the computer to understand. This is where a programming language's syntax comes into play. Now, just as if you were learning a real language, learning a computer language can be very similar. Some have different styles that may seem odd. Some may make you use weird or abstract concepts which may be confusing, and like all languages, programming languages have a set of rules that you must follow when writing code in that language, and at the forefront of those rules is grammar. Programming grammar is referred to as syntax, and is very similar to real-world grammar. Each programming language has its own syntax or rules that you have to follow to a T if you want your program to run correctly, just as if you were speaking in real life. These can be things such as how you type out certain functions, what you put at the end of a line of code, and how you set up certain functions. Each language is unique in its syntax, and while some may share similar rules, all will have some quirk which makes it stand out from the rest. Syntax is something that catches a lot of people off guard, since many expect every programming language to follow the same set of rules. But as we spoke about in the last segment, because each language is specialized for a specific task, each needs its own set of rules to function. Breaking or disregarding these rules will result in an error, just how breaking or disregarding rules in real life will result in an unintended message. As an example, if you wanted to do something simple such as initialize a variable, which is something that we haven't covered yet, but the example is still relevant. In Java, you'll notice how we have to specify what type of variable we are defining, in this case an integer, and also add a semicolon after the statement. In Python, we don't even need to define that we are trying to create a variable and just have to type what we want to create. And in JavaScript, we just specify that we are making a variable, but we don't include what type of variable we want to make, like in Java. Even in this simple example, you can see how much a syntax matters when learning a new language, since while the goal of our program remained the same, which was to define an integer with the value 3, all the programming languages shown took different approaches. All these languages require that you follow this syntax because remember, computers are extremely dumb. If you forget one semicolon or misplace a character, the entire program will not run and send you back a syntax error, which is something we'll talk about later. Think of this as if you forget a comma in a sentence and the entire context of what you're trying to say gets misinterpreted. For example, in the sentence, "Let's eat, Grandma," if you were to forget that comma, while it may seem like a small mistake, it changes the entire context of the sentence, making it sound like you're going to eat your grandma. The same rules follow for programming. If you forget a semicolon, the entire context of your program could be corrupted and misinterpreted by the IDE. Now, another thing which makes IDEs so useful is that they will let you know if and when there are syntax errors in your code. Syntax errors, of course, being parts of your code which do not follow the same rules what we talked about previously. The IDE will tell you where in your code the error is, and also won't let you run your program until the error has been fixed. Because of how important syntax is to writing code and learning a new language, it's recommended that you learn the rules and syntax of a language before beginning to write complex programs in that language. Most of the rules are tedious to learn but easy to master, and as soon as you can do that, you'll be able to easily identify syntax errors and take care of them easily, and be writing code in no time.
That covers the basic gist of syntax and programming rules. So now that we know how to write code and where to write code, we next need to cover what happens after we have typed out our program and run our code. Because writing a piece of code for a game or for a database is cool and all, but after the computer interprets the program, how will we know what's happening and whether or not it's working? Well, programmers do this by looking at the console. The console is a text interface within your computer that us programmers can use for a variety of different purposes. If you remember, a short while ago we showed a picture of a basic IDE, and one of the main parts of the picture was the console. The main use of the console is to output text from the program. This is usually done by using a print statement. A print statement is a command that does exactly what it sounds like. It prints text to the console. The print statement is the first piece of actual code we've talked about in this series, and it's about as simple as it gets. The print statement, despite its simplicity, is one of the most important functions in programming and exists in some form in just about every programming language. The most basic thing you can ask the print statement to do is to just simply make it say something. This is done by instructing the console to print, and then include whatever you want to be printed inside the parentheses. For example, in Python, the segment of code print hello world will cause a message reading hello world to appear onto the console. Pretty neat. The print statement is also vital for viewing and interpreting the computer's output from a program. For instance, if you tell a computer to run a simple calculation, for example to determine what 4 plus 3 is, it will run the program internally and compute an answer. However, what is the purpose of having the computer run this program if you will not be able to tell what the result is? Instead of simply telling the computer to perform this calculation, instruct the computer to print the output of the program to the console, and upon the program's completion, 7 will appear on the console. As you can see, the console allows us to easily print information out to the developer for a variety of uses. It is important to note that the print statement varies depending on the programming language being used. For example, in Java, there are multiple versions of the print statement depending upon whether you would like a line break after the printed text or not, as well as specialized print statements which make your code run more efficiently. Also, the general syntax of using a print statement and certain nuances of its function can change between languages. However, you can generally rely on it to carry out the same overall function, as it is a foundational statement for programming in general. All of its functionality makes the print statement, along with the console, a very useful developer tool. However, it is important to remember that that is all it is, a developer tool. The console is not really meant to be viewed by the end user of your program. It tends to be hidden away behind the scenes, and other methods of displaying information, such as displaying text, graphics, or images, are used to convey information to the user instead. Think of it like this. When you are using your phone, you see the console in none of the programs you use. So while you can use the console to give yourself information about how your program is performing, don't try to implement it into the final product because it fundamentally just isn't meant for that. Overall, remember to use the console to its fullest extent when writing and fixing problems in your programs, as it is a great tool to use to tell how your program is performing behind the scenes.
So now that we know a bunch of information about programming languages and how and where to write them, along with the print statement under our belts, Let's go over some intuitive things that the computer can do all by itself, without you having to tell it how to. More specifically, we'll be covering some basic number mathematics, as well as string math. Starting off with basic mathematics, the computer already knows how to do simple arithmetic. This includes addition, subtraction, multiplication, and division, all of which are represented by the symbols shown on the screen now. In any IDE that you may install, you'll be able to print out the answer to simple math problems using the print statement, which may seem counterintuitive because why would you use the computer to do math when you have a perfectly good calculator on your phone? But you have to remember that computers are dumb, and anything we want a computer to do, we have to build up from scratch. Basic arithmetic, while simple, helps out in almost any program you may write. For example, if we wanted to build a basic calculator app, we'd need to utilize this functionality in order to correctly display the answer to an arithmetic problem when our user tries to add, subtract, multiply, or divide two numbers. Now, in addition to the 4 basic math equations, most programming languages include an additional operator known as modulus. If this is your first time hearing this word, don't worry, since it's not usually taught in math classes. Modulus allows us to get the remainder of a divisional operation. For example, when we take 10 modulus 3, we are essentially telling the computer to take 10, divide it by 3, ignore the actual answer, and just give us the remainder of the operation, in this case 1. Since when we divide 10 by 1, the answer is 3 remainder 1. The 1 in this case is what gets printed out to the console. If there is no remainder, say in the case that we take 50 modulus 2, since the remainder is 0, the function would return 0 if we were to print it out to the console. This can be extremely useful in many cases, the most obvious being if we want to determine whether or not a certain integer is even or odd. If we take a certain number, modulus 2, and it returns 0, then we know that is even, because any number divided by 2 will always result in a full answer without a remainder. But if the system returns 1, then we know that the integer is odd. You will find yourself using the basic math operators a lot more than you think, so it's good to keep them in mind when writing your program. Now, not only can our computer work with numbers, but it can also work with strings. Strings, by the way, are just another way to say text. For example, hello world is a string, the letter A is a string, and anything enclosed by quotation marks is denoted as a string in programming languages. We'll cover more about strings in a bit when we talk about variables, but for now, let's continue. We already talked about printing strings to the console, but let's say we're making a game, and we wanted to print out the statement, game over, 4 was your final score. Now, while we could just make a string that says that exact phrase and print it out to the console, in some cases it would be more useful to print out the actual integer value, especially in the case of a game where the score can change each time you play, because score definitely isn't always going to be 4. Well, we're also able to print out multiple strings of text, and even integers, by adding them together in the print statement. This is known as concatenation. Continuing with our score example, if we wanted to print out the statement, game over, 4 was your final score, using 4 as an integer rather than a string, we could do this by breaking down the statement into 2 strings and an integer like so. Print game over plus 4 plus was your final score. We of course begin with the print statement, which again will be different across all languages, but in this case we're using Python. Inside the print statement, we start off by printing the string game over. Now here comes the important part. From there, we use a plus sign and add 4 to the print statement, just like if you were adding 2 numbers. Then we can repeat this process with another plus sign for the final string was your final score, and we're able to print out the entirety of our statement easily. Doing this, we can easily print out multiple different strings and integers together in one print statement. We could also combine the 2 lessons we've learned thus far and do something such as game over plus 4 plus was your final score. In the case, let's say, where you have a game which gives you a base score and then 4 points for a certain task that you completed. This demonstration also displays another important part of programming, which is that oftentimes, to get your program to be the most efficient, you have to combine aspects of code. Now, it's important to note that the computer will take whatever you put in the parentheses and print it out, character for character. So oftentimes, programmers will forget to add a space onto the end of their strings. This can result in a small mistake in which the string from the previous example would be printed out as if to say, game over 4 was your final score, which isn't that appealing when displayed on the screen to the user. So it's a good practice to always put a space after and before your strings to make sure this doesn't happen and your string doesn't end up like that. Another important thing to note is the difference between for in quotation marks and for without quotation marks. Now, for in quotation marks is treated as a string rather than a for without quotation marks, which is treated as a number. This may not seem like a big deal, but again, computers are dumb, and if you try to do math with a number in quotation marks, it will return an error because the computer doesn't understand that you're trying to perform the operation on a number, and it thinks you're trying to add an integer to a string, which is a big no-no in programming when you're adding numbers. So when you're programming, make sure to make a mental note of whether or not you want to make something an integer or a string, because that type of stuff makes a big difference. Alright, that concludes our segment on the base power of computers.
Now next up, we're going to be covering one of the most important components of computer science, so make sure you pay attention, because next up we're going to be discussing variables, what they are, and how we use them. First of all, what exactly is a variable? A variable is simply something that can store information and can be referenced and manipulated. Think of variables like a cardboard box. Cardboard boxes serve as a means to store items in them, which can be changed out, replaced, and modified. Variables are like cardboard boxes that store information for the programmer to reference or manipulate. Each variable simply has a type, a name, and a piece of information stored inside of it. The type and piece of information will be covered next, and the name is simply a name for the variable. Think of it as writing out a label on the cardboard box in Sharpie. Now, there are many different types of variables that a programmer can use, but right now, we will just be covering what are called primitive variables, which include integers, booleans, floats and doubles, strings, and characters. We'll start off by talking about an integer. An integer, or int for short, is as simple as it sounds, a variable that can store an integer value. This includes all whole numbers from negative 2,147,483,648 to 2,147,483,648. Notice how I said whole numbers. Integer values can not and will not hold any decimal values, so keep that in mind when using variables. Secondly is a boolean. A boolean is a very primitive variable which can store a value of either true or false. Boolean variables can only hold these two values and are extremely useful for conditional statements, which we will cover soon. The next two types of variables are floats and doubles. Both of these variable types are floating point data types, which essentially means that these variables can store numbers with decimal places. Whereas integers values cannot hold decimal values, floats and doubles can. The main difference between the two is that a float variable can store numbers of a precision up to 32-bit, while doubles can store numbers with a precision up to 64-bit. Essentially, a double can store more decimal places than a float, so it all comes down to how precise you want the variable to be. Up next we have string variables, which are like the strings we've talked about beforehand, except stored somewhere in a value. String variables can store strings of letters, which are just words and sentences. Strings are useful for displaying text and storing input information. Strings can also be concatenated together to form combinations of string variables and pre-written strings. This can be very useful for outputting information in a readable format for the user. For example, imagine we have a string called name. The code asks for input and stores that string of text in name. To output this information to the user, rather than simply displaying their name, you can add the phrase your name is and make it into a sentence by concatenating your name is plus name plus period. This makes it easier to read your code, while also adding variability to your code, which always makes things more interesting for the end user. Finally, we have char variables. Char stands for character, and just as the name suggests, they can each hold one character. This is useful when a programmer wants to read one button press or one character in a string without using a string variable. A specific example is making a game that is controlled by the keyboard. The program needs to recognize the character that is pressed and translate that into carrying out some function. Now, strings can also hold one character, but chars can't hold more than one character, so keep that in mind when defining variables. Now, why are variables so useful? Well, being able to store information in a format that can be easily referenced later is essential for any good program. Oftentimes in code, you're going to want to keep track of things such as a user's name or score, and so by creating a variable called name or score, you can store this information in the variable and then reference it, add to it, or modify it. Also, many times, the program will want to take input from the user, which cannot be pre-programmed into the code, and thus a variable is required to store the information. A program may also rely on factors that will change as the program progresses, in which case a variable is once again required. Also, taking these variables and manipulating them is quite necessary for carrying out many of the tasks you want a program to carry out. For instance, multiplying int variables or concatenating string variables. Overall, variables are the backbone of any good program, and you'll find yourself using them often if you want a clean and efficient code. So it's best that you learn what types of variables you need to use and when.
So now that we know all about the different variable types, and we've talked about them a little bit, we're going to delve further into what happens when we actually define or create a variable, how we reference them, and how we can manipulate them for our programs. To start, let's go over what happens when we actually define a variable. Now, when we write a line of code which initializes a variable, and that code is executed, the computer essentially creates a little space in memory that stores your variable name and its contents so that it can be referenced later. Going back to our cardboard box example from the previous segment, think of this as if you had your own storage facility, and you make a new cardboard box labeled name, and inside of it you put a piece of paper with the word null pointer exception on it. Now, anytime you want to know the contents of your name box, you could simply look inside and see that it has the contents null pointer exception. This is what the computer does, except the storage facility is the memory in your computer, the box is a variable, and the contents of the box are whatever the variable is set to be equal to. Anytime you want to know the contents of the name variable, you can simply call it, and the computer will pull the information that is stored in that variable and use it how the user sees fits. Another thing to note really quickly is that you can actually make a variable without putting information inside of it. This would simply be like if you built up a new cardboard box, gave it a label with a Sharpie, but just didn't put information inside of it. You're simply saving that space in your storage facility for later. This could be maybe because you want to store information in it later down the road, or if you're going to use it to store information given to you by the user, in which case you can't give it information since you don't know what the user will input. Just a note that if you try to reference or point to a variable which does not have any information in it, you'll get what's known as a null pointer exception, which, despite being an amazing name for a YouTube channel, is something you generally want to avoid when programming. Now, programming languages allow us to do some pretty cool things with these boxes that we've created. For example, let's say we created a second variable called channel name, and instead of setting it equal to null pointer exception, we instead set it equal to our already created name variable. This doesn't create a space in memory for this new variable, however it simply points to the same location of memory we have already created for the name variable. Going back to our storage facility example, this would be like instead of creating a whole new box labeled channel name and storing a sheet of paper with the word null pointer exception on it, we instead simply added another label below the name box entitled channel name. Now we have two variables which point to the same contents, that being the string null pointer exception. We usually do this to save space in our code for things that we know are going to have the same value. Variables can also be updated throughout your code. For example, let's say you had an age variable, and inside of it was the integer 17. Then, you celebrated a birthday and wanted to update your age. All you would have to do is reference the variable and set it equal to whatever new integer you want the variable to hold. In this case, 18. This would be the same as having a box labeled age with a sheet of paper reading 17 inside of it, and then taking that piece of paper out, erasing 17, replacing it with 18, and then placing it back in the box. Doing this, we are able to easily update the contents of our variables throughout the code as things dynamically shift. As another example, if you were making an RPG, your character would likely have stats such as attack, defense, mana, etc. As the game progressed, you could continuously update the variables so that the player could get more powerful the further along that they went through the game, and you wouldn't have to create new variables. You would simply need to just keep grabbing that box from your storage facility, erasing and replacing the numbers on the piece of paper, and then continue along with your code. Just keep in mind that these variables are nothing more than places in memory in which a certain value is stored, so we can easily update the numbers, and their place will remain constant. After the code has run its course, the place in memory is deleted until you run the code again and the program dedicates space for the variable again. Each time you run the code, you're making new boxes in your storage facility, and at the end of the code, you destroy them all to make room for the new boxes next time. Another cool thing you can do with integer, float, and double variables is add them, subtract them, divide them, multiply them, and even modulus them. For example, if you were making a calculator app and you stored the first number the user entered as number 1 and the second as number 2, you could then multiply num1 and num2 together and either print them or store them in a new variable entitled result. Then, each time you run the program, the user could input new numbers into the num1 and num2 variables, and they would simply be set to those new integers that the user inputted, and return the result that corresponds to those specific numbers. This allows you to keep easy track of which numbers are which, and what's going on in your program, which is extremely useful. Also, while you cannot subtract, multiply, divide, or take the modulus of strings, you are able to add them, like we said previously. Let's say you had a string str1 with the contents hello, and a string str2 with the contents there. You could add str1 and str2 to create a string that had the contents hello there, either storing it in a third variable or printing it out to the console. The last topic we'll be covering on the topic of variables is the naming conventions of variables, which albeit may seem odd, but it's extremely important when trying to read your code, so we'll be covering it now. Now, variables have to be one continuous string, and so if you wanted to make a variable that stored the player's score, you'd have to find some way to combine the words player and score, since you can't have the phrase player score be the name of a variable. All programmers have their own personal preference when it comes to naming variables, but the one we'll be using in this lecture is called camel case, which is the process of not capitalizing the first word, but capitalizing every word that follows it. Going back to the player score example, using the camel case method, the variable would be called player score. This allows us to easily see and identify each word and becomes really useful for long variable names, like the player score before the final boss. Whereas if we just type it out without camel case, it would be really confusing and hard to read. This will help you out a ton when we start finding bugs in our code and need to quickly scan through our program to figure out what is wrong, and adds to the overall readability of the program. Other programmers might use different naming conventions, like using underscores to separate the words in a phrase, but for now, in this series, we'll be sticking with camel case.
Next, we'll be moving on to conditional statements, which at their core are statements that change the path of our code depending on certain conditions. For the sake of keeping things simple, for this section, red lines will connote that our code will not be following the specific path, and green lines will mean that our code is following the path. The main type of conditional statement that programmers use is the if statement, and this will show up countless amounts of times in any program you write. It is as simple as it sounds. If some condition is true, and usually that condition will be enclosed by braces, then carry out the instructions located within the if statement's brackets. Else, do another thing. Now, brackets are used in most programming languages to indicate a segment of code which will run. It works like this. If the condition in parentheses is true, then all of the code contained within the brackets will run, and if the condition within the parentheses is not true, then it will skip over all of the statements within the brackets. A quick note is that while this is the case with most programming languages, some, like Python, use colons and whitespace to determine where a piece of code starts and ends, but for the sake of this series, we'll be using curly braces. Now, the condition within the parentheses can take on thousands of different forms, such as if the value of the string variable name is equal to Stephen, or if the player's score, stored in an int variable, is greater than 5. The list goes on and on. Each of these statements is evaluated as a boolean, which you will remember from when we talked about variables, is either true or false. If the boolean is true, we run the code inside the curly braces. If it's not, we pretend everything inside the curly braces never existed and move on with our code. The if statement comes with two more additional statements that can go with it, else if and else. Else if is a conditional statement used directly after an if statement, and carries out mainly the same function as an if statement. However, the else if statement will only be evaluated if the preceding if or the preceding else if statement is bypassed due to its condition being false. So we would run through it like so. If something is true, we would run the code inside of that statement's curly braces. Else, if that something is not true, but another statement inside of the parentheses is true, we would then run that code segment. And if neither of them are true, we would skip both segments of code and move on in our program. This can be a hard concept to wrap your head around, so let's do an example. If we had a program that evaluated the if statement if age is equal to 10, we could then have a statement under that which stated else if age is equal to 12. Now, if the age variable was 10, which we can see from the example that it is, then the code immediately following that conditional statement in the brackets would run. The else if statement we made will not even be tested, since we know that it is going to be false. and thus the print statement inside of that conditional statement's brackets will be ignored, and the code will move on to the rest of the program. Now, for example, let's say we change the age variable to be 12 instead of 10. Now, instead of the first conditional statement being true, it actually evaluates as false, since age is no longer equal to 10. So what we do now is first skip over the print statement, which prints out that age is 10, since it's not. And then we evaluate the else if statement. We check if age is equal to 12, which again it is. And so now we run all the code inside of that conditional statement before finally moving on to the rest of our program. So, as a review, we check the initial if statement. If it's good, then we run all of the code within that if statement's curly brackets and move on with our program. If the initial if statement is not true, we then move on to any else if statements and evaluate if those conditional statements are true. We can have as many else if statements as we want, although this could lead to clutter amongst your code, so we'll talk about some alternatives later to help this out. Now that takes care of the if-else statement, so now we'll move on to the else statement. The else statement, once again, comes after an if or an else if statement, and will carry out its instructions no matter what, as long as the preceding statement/statements are evaluated as false. If we went back to our previous program, we could add an else statement, which would only have the code in its brackets run if the age variable wasn't 10 or 12. This will catch all cases of the program that didn't fit into our parameters. It's good practice to always have an else statement at the end of your conditional statements to catch any weird cases that may come up in your program. Now remember back to the fact that we could have thousands of else if statements. After a while that can get pretty cluttered, and so another very useful conditional statement which helps circumnavigate this problem is a switch statement. A switch statement is functionally similar to many if and else if statements together. You write a switch statement in the form of switch variable, and then below that you write out how many cases the variable could be. For instance, if we wrote switch var, and then under it we could write out 5 cases that the variable var could be, and then the instructions listed under each case would be carried out if the var variable would be equal to that case. Now switch statements are different since instead of using brackets, they use a colon to signify the start of a set of instructions and a break statement to end them. This is very useful because you are able to essentially use many if and else if statements without having to write nearly as much. In switch statements, you just always have to remember to include a default case at the bottom of the expression to denote any and all cases that don't meet the above requirements. This simply catches all the inputs that don't fit within the program's main cases. It's very similar to an else case at the end of an if-else chain. Now, why are these statements so useful? Well, many times, programmers want their programs to function differently depending on different conditions. For instance, a program could function differently depending on the information that the user inputs, such as allowing a user to use a program or not use a program if they are above or below 18 years old respectively. Or in, say, a video game, if a user's experience is above a certain threshold, we might want to give them harder opponents to battle. Another example could be a program which changes the color scheme depending on the time of day. Or even more simply, if a user presses a button that is meant to move on to another screen in an app, the programmer would only want that app to change screens if the user clicks that button. A program without conditional statements would do the same thing every time, and would be very primitive compared to one that can change depending on its conditions.
So now that we know how to make and use variables, how to compare them, and what we can do with those comparisons, let's move on to another foundational concept of computer science, and that is arrays. Now we've already talked about variables, and how great they are for storing singular bits of information for making our code more simplistic. But one of the biggest drawbacks that comes with variables is their inability to hold more than one piece of differing information. For example, let's say you're making an app which allows a user to create a grocery list. Well, there's no real easy way to create lists using variables, because it's not like you can have one variable store the names of 6 or 7 different food items. Remember, we can only put one piece of paper in our cardboard box, no more. And besides, even if you were able to add multiple items to one string variable, you would still have a lot of trouble doing simple tasks you might want from a list, such as searching through it, splitting it, or even deleting items from the list when you're done with them. This is the problem that using arrays solves for us. An array is, as you may have guessed by now, a list. You can have an array of integers, an array of strings, and even an array of other arrays, which is something we'll cover in a minute. Programmers use arrays when they want to store a lot of variables containing information that is all related to each other, such as a grocery list or a high score list in a game. Think of arrays as a column in Excel or Google Sheets. You have the title at the top, and then below it are a bunch of bits of information which all relate back to the title. Arrays are super useful when programmers want to store a lot of information that can be easily searched through, because programmers have developed methods of breaking down and using arrays to find specific information in arrays full of thousands of different variables. As an example to show just how useful arrays are, let's say you're a startup company that owns an app that has 100,000 users. Every time a user wants to create a new account, They input the username they want, and then your program will have to check to make sure the account name hasn't already been taken. Doing this requires you to search through the information of all 100,000 of your users to see if that username has an account with your service. An array would be able to contain all of this information and make it easy to search through and find out if the account name has already been taken, with little to no delay. Now, the single most important thing to note about arrays is how you reference each element of the array within them. Let's create a basic array called numbers, and inside of it put the digits 1 through 10. Now, when we want to refer to each cell in this array, we would call upon its index. An index is just a fancy way of saying that number's place within the array. Now, you would think that the first integer in this array would be the first index, the second would be the second index, and so on, but that's simply not the case. In computer science, programming languages refer to the first cell as the 0th element in the array. This means that if we were talking about our array of numbers we just made, the number 4 would actually be in the third index, 5 would be in the fourth, and so on. So instead of starting our count from 1, we start from 0. It's extremely weird and confusing, but it's one of those programming quirks you're going to have to memorize and commit to memory. If you were to not follow this nomenclature and refer to the last element in this array as the 10th, you get what is referred to as an array out of bounds error, since you're trying to reference the 10th element, but there is no 10th element. What you're actually trying to do is reference the 9th element. Another extremely important thing to note about arrays has to do with their size. When you initialize an array, you can do it in either one of two ways. You can either populate it with the elements that you want contained in the array right then and there, creating and filling the array at the same time, or you can define how many elements you want the array to hold, essentially the array's size, and then populate it with elements later. This is because when we initialize an array, it creates a space in memory that has the size of exactly what you give it, no more and no less. This is great for when we want to access elements in the array because we can do so instantaneously because the computer knows exactly where in memory the array is stored. But the one downside is that we can't increase the size of the array later on. All array sizes are final. Think of this like setting up a bookshelf with books. By populating a bookshelf with a certain number of books and then moving on and filling the next shelf with different books, we have no way to go back and add books to that first shelf without shifting everything over. Once we decide how much space to dedicate for an array in this case, there's no way to add more space. Once again, because this is extremely important to remember, this means that once an array has been defined, there is no way to change the size of it. If you have an array titled names with a size of 8, and you try to add another name to the array, you will receive an error. So be careful when messing around with array sizes. Of course, you can always go back to the start of your code when you initially make the array and allocate more space to it, increasing its size, if you find out that you need more space to hold items. But once it's defined, you cannot change its size through conventional methods. Another small thing I want to touch upon really quickly is that when you initialize an array, you must determine which type of array it is right then and there. For example, you have to specifically say it will be an array of strings or integers when defining it. And also, you're not allowed to mix and match, meaning that you can't have an array full of integers with a few strings and some doubles thrown into the mix. They all have to be the same type. Now, the last thing we're going to cover on arrays is a little funky, and that is the practice of putting arrays inside of arrays. If you make an array of arrays, it is referred to as a 2D or two-dimensional array. Think of these as matrices if you have taken an algebra class before. Now, if you haven't, think back to our Google Sheets example, but instead of using columns, we would add rows as well. So now each element in an array wouldn't simply just be a string variable or an integer variable, but an entirely new array with its own set of values and elements. The way we index these is mostly the same, except we would have two numbers to index instead of one. We start with the row and then the column. So a number in the position 0, 2 would be in the first row, 3 columns down. In this case, the name Clint. A number in the position 1, 1 would be 2 rows down and 2 columns across. In this case, the name Chris. You get the idea. Now you can also make three-dimensional arrays by putting an array inside of an array inside of an array, but that's a little above what we're going to be covering, so I'm going to cut it off there.
Next up, we're going to be talking about loops. So what exactly are loops? Next up, we're going to be talking about loops. So what exactly are loops? Next up, we're going to be talking about loops. So what exactly are loops? Next up, we're going to be talking about loops. So what exactly are loops? Next up, we're going to be talking about loops. So what exactly are loops? Well, as you could probably tell by that statement right there, a programming loop is a statement that is used to run certain instructions repeatedly, just like how the opening statement of this topic was repeated 5 times. Loops are very useful for a variety of reasons. For instance, imagine you want to print something 15 times. Sure, you could just copy and paste the print statement 15 times, but this is really annoying to have to do, and becomes even more unrealistic when that number goes up to, say, 100 or so. Now, what if instead of rewriting the same instructions over and over again, you could simply place the print statement inside of a loop, and it will occur as many times as you would like. Now that's the power of loops. With loops, we're able to repeat parts of code multiple times. Now there are 3 different types of loops that we will be discussing today, and up first is the for loop. A for loop is very useful for situations like the one described above, where you would like to carry out a certain set of instructions numerous times. The syntax for a for loop varies depending on the language, however it usually consists of 3 parts: an integer value, a condition which the integer value must meet in order to exit the loop, and an operation to modify the integer value after the instructions inside of the loop are completed. Each time the for loop runs, the operation you set will be performed on the integer, and as long as that integer still meets the condition you set, usually being greater than or less than a constant value, the for loop will continue to run. Eventually, when the integer has been modified by either increasing or decreasing it to the point where it no longer meets the condition, the for loop will terminate and the code will continue to run. For example, let's say our integer value is I and we set it equal to 0. Then we set the conditional statement as I being less than 3. So basically we're saying that as long as I, the variable we just created, is less than 3, continue running the instructions contained within the loop. Finally, we make the operation I++, meaning each time the loop runs, we will increase it by 1, and inside of the loop, let's just put a simple print statement. Now, let's run through the for loop. We start with I equals 0. 0 is less than 3, so we enter the loop and print out hello world. Now that the instructions are done, we add 1 to I, making it 1. Moving on, 1 is again less than 3, so we once again enter the loop and print out hello world. Again, we add 1 to I, making it 2 now. 2 is still less than 3, so we enter the loop again and print out hello world. Finally, we add 1 to it once again, and it becomes 3. 3 is not less than 3 though, it is equal to 3, and so we don't enter the loop and it terminates, moving on to the next segment of code. This is a simple example, but you can extrapolate it across programming to fit your needs. Now, when using a for loop, you have to make sure to set up a condition that, given the initial integer value and the operation, will at some point not be met, to avoid creating an infinite loop and crashing your program. An infinite loop occurs when you give a for loop a condition which will always be met given the parameters of the program, and so the software crashes. For example, a for loop beginning at 10 and checking if I is ever less than 0, and then adding 1 to I at the end of the loop will never terminate since I will just increase infinitely. After the for loop is the very similar for each loop. A for each loop, or a for in a list loop in Python, is used for iterating through arrays or lists. Essentially, the loop will go through each element in the array and carry out some set of instructions for each value. If you would like to read all of the elements in an array and compare them to some value or perform some operation on them, a for each loop is extremely useful. So for example, we could have a for each loop which iterated across an array and simply printed out the value of each array location. Next up, we have the while loop. A while loop will continually carry out its instructions while a conditional statement given to it is true. This can be as long as a certain variable is true, as long as a number is less than another number, or while a value is still equal to another value, for example. While loops are different than for loops in that the loop is not contained within one statement, but stretched out and will continue to run as long as this condition is true. Like a for loop, you could make the condition such that it will eventually return false and exit the loop. However, while loops will not crash your computer should you create an infinite loop. In fact, it is very common for while loops to run infinitely, as, for certain programs, you would like the program to continually be iterated through instead of running once, all the way through until you exit out of the program. When programming a game, for instance, a while loop would be used to iterate through your code, continually refreshing the screen as the game runs. From there, you could perform operations on the screen to make the game playable. Creating an infinite while loop could be done by simply using the syntax while true, as the condition true will always be evaluated as true. Finally, I'd quickly like to cover the extension of a while loop, the do while loop. Do while loops are very similar to while loops, except they will carry out their instructions at least once, even if the condition is false, and then will carry on like a basic while loop. Essentially, the conditions inside of the loop will run at least once, and then if the condition is still met, they will run again and function as a normal while loop would. As you can see, loops in their many varieties have some extremely useful functions. Using them, you are able to perform an operation many times in a row, you can iterate through arrays and lists, and overall decrease the clutter of your code.
Next up, we're going to be taking a break from learning about common programming statements and dive into what happens when the code we write doesn't work.
More specifically, we'll be covering the different types of errors that can occur when you're programming, and what causes them. Now, when you're writing code, you have to understand that things aren't always going to go the way you expected them to, and sometimes the program doesn't always work as you had intended it to. We programmers call these errors, and while annoying, they are always going to come up in computer science, and so it's best to learn what they are and how to deal with them. Often referred to as bugs, errors in scripting languages can be narrowed down to one of three types: syntax errors, runtime errors, and logic errors, all three of which we'll be covering in today's video. To kick things off, let's talk about syntax errors. These are usually the easiest of the three to solve, since they are oftentimes something that can be fixed within seconds. If you remember back to earlier in the video when we talked about syntax and programming rules, we said that if you were to break the programming rules, or syntax, that it would result in an error. Well, that's what syntax errors are. Parts in your program where you fail to meet the programming rules, and so the computer doesn't know how to interpret your code. This can be anything from forgetting a semicolon at the end of a statement in Java, accidentally defining a variable with 2 words instead of 1, or even just misspelling the word string when you're trying to define a string variable. Lucky for you guys, these errors are extremely easy to fix, since you just need to figure out where the error occurred and what the syntax rule you broke was. Now, thinking back to IDEs, we mentioned that IDEs are so useful because they do precisely that. They underline the syntax errors and usually provide helpful hints as to how to fix them. Think of syntax errors as small misspellings or grammatical errors in an essay you're writing. Annoying, yes, but not the most infuriating things. Another useful thing about IDEs when it comes to syntax errors is that the program will actually restrict you from running the code unless all syntax errors are cleared, making them even easier to identify and fix. The second type of error we will be covering is the runtime error. These errors don't show until you actually run the code, hence the name runtime error. Runtime errors are usually caused by a statement in your code that seems logically sound, but the computer physically has no way of computing it in a reasonable amount of time. The most common of these errors is one which we've already talked about, the infinite loop. As a refresher or an example, think of an infinite loop like this. Say you sat your friend down in front of the TV, put it on The Office, and told him he could leave as soon as Michael made a "that's what she said" joke. Seems pretty simple, right? Wrong, because instead of putting in The Office, you put in Friends on Blu-ray. No Michael, no inappropriate joke, meaning your friend would be sitting there for the rest of his life. This is basically what happens with a computer. You give it some condition that it has to complete before the program can terminate. However, you give it no feasible way to finish the task. This puts the computer in error mode, and most likely will crash your program, as the computer desperately tries to complete the condition you gave it. As a computer example, if we try to have a program terminate when integer I is no longer greater than 99, but I is initially 100 and only ever increases, the loop will never terminate, and the program will crash. To avoid these, you generally want to think through the flow of your code before running it, especially with loops, to make sure that all of your statements can be completed by the computer. Carefully planning out your code before you begin writing is an extremely useful practice, and something we'll be covering towards the later part of this video. The final type of error that we will be covering is a logic error. This error is also pretty self-explanatory. A logic error occurs when the code runs smoothly without any runtime or syntax errors, but the result that you get just isn't what you wanted. For example, let's say you had a calculator app, and you wanted to instruct the program to add 2 numbers, except it multiplied them because you used the multiplication symbol on accident. This leads to the sum being 36 instead of 13. Nothing went wrong with the code syntax, or runtime-wise. The code runs just fine, it just doesn't work as you had intended it to. These are often the hardest types of errors to debug, since most of the time you'll have no idea why the code isn't working, and certainly not any idea of how to fix it. This is why it's a good idea to test your code incrementally. Don't wait until you've been programming for an hour before testing your application, or else you'll run into a lot of logic errors. Logic errors can be extremely infuriating, and could cost you a lot of time, making them a huge pain. But if you know how to effectively debug your code, you'll be just fine.
Speaking of debugging your code, that brings us straight into our next topic, which is how to debug your program. Now, let's say you've written a program. You think it's ready, and you're ready to test it. You've been working hard on this, and you're excited to see it in action. You run the program, and wait for it to run smoothly and efficiently. Only it doesn't work. You've encountered one of the 3 errors we just mentioned. You really want this code to work, but how? This is where debugging comes into play. If the code is giving you an error, then the first thing you should do is read the error. Oftentimes, for syntax and runtime errors, the IDE will print an error message out to the console. See what line or lines it points to, since those will be the lines that the error occurred, and see if you can understand and fix what the problem is. If the error isn't clear, or you've never heard of it, then try Googling it, as there are many websites out there such as Stack Overflow, which serve as forums to ask and answer problems with code. Chances are, if you've had a problem, someone else has had the same issue, and there is likely a tested solution. Usually, when a syntax or runtime error pops up, you should be able to find a fix for it fairly easily. However, as I said before, the issue may arise from some loophole or oversight in the code you hadn't planned for beforehand. Maybe you did something as simple as multiply two variables instead of adding them. These are logic errors we talked about previously. These problems usually won't have red text show up to explain what went wrong. You'll have to figure it out yourself. Now, there are a few different strategies that you can use in order to track down and fix a logic error. First, you could use print statements and the console in order to determine where the code is going wrong. Imagine you have a conditional statement that will run one segment of code if an integer x is greater than 5, and will run another segment of code if not. If, in your program, x is supposed to be greater than 5 when the program reaches this conditional, but for some reason the program is still printing out x is small, you could use a print statement to help. For this problem specifically, you could place the print statement before the branch of the conditional that would print the value of x. Now, when you run the program, you know exactly what the computer is thinking. Printing out the value of x just before the if-else statement will let you know if the variable has the value you wanted to have, and if it doesn't, you know that somewhere above that conditional something went wrong and x was set to a value you didn't want it to. In this case, x is equal to 2, which is why x is small is being printed out. Now that we know what the problem is, we can track down where and when in the code we modify x in order to solve it. Use print statements to determine where your program goes wrong, and then try to track down the cause of these issues and solve them. If you use this strategy, make sure you end up deleting the print statements afterwards to avoid clutter in the console. The situation described above could also be solved using a breakpoint. A breakpoint pauses your program when the line you placed the breakpoint at is reached. If, say, you would like the program to run through a certain conditional and set a variable based on that conditional, but you are unsure if this actually happens in your code, you can place a breakpoint inside the conditional path that you expect to run. Upon the breakpoint being reached, the program will pause and wait for you to continue it through a button press. This signals that the spot in the code where the breakpoint was placed, in this case the correct conditional path, has been reached by your program. You can then continue the program knowing that this was or wasn't where the error in your code occurred. Breakpoints can be used in conjunction with print statements in order to both pause the program and perhaps view the values of your variables at the moment in time to give yourself all the information you could want. You can also have multiple breakpoints to help slowly work your way through your program and determine where an error has occurred. A combination of these two strategies will help you easily determine where in your code you have incurred a logic error. Next, let's go over what to do if you think you have tracked down the section of code that causes the problem. You may think you should delete it, but it's likely you put it there for a reason, and you don't want to lose all that work if you don't have to. Firstly, try commenting it out. Comments are used to mark up code and explain their surrounding sections, but they can also be used to debug. Anything that is designated as a comment will not be read by the program as code, and will be skipped over. Essentially, it becomes something that is only there for you, the programmer, to read. The syntax varies from language to language, but it usually involves placing some symbols before or around the code you would like to be commented. Examples of how to comment in different languages can be seen on the screen now. Also, when you comment something, the IDE will grayscale that line of code, making it extremely easy to determine what's commented and what's not. Commenting code deletes it in the computer's eyes without actually deleting it. If a problem is present before you comment a section of code, but it is gone afterwards, then that section of code is the culprit. If you comment part of the code out and there are still issues, then move on to another section until you find the culprit. Once you do, you can tweak it until it works as intended, or delete it entirely, and you'll have a fully functioning program once again. Now that we've talked about what to do if you've encountered an error, and a strategy on how to find and fix it, I'd like to talk about some strategies you can use to avoid errors in the first place. Firstly, back up your code frequently. In the event of the code completely bugging out and you being unable to fix it, you will want the ability to revert to a previous version where the code was still working. If you save frequently enough, then you will probably not lose too much work. Version managers like GitHub or Subversion can help with this, as they back up code to an online cloud service in which you can easily pull previous versions of the program from at any point. Also, on top of saving, run your program frequently to ensure that the current version works as intended. This accomplishes two things. First of all, it prevents you from saving a backup that doesn't work. Secondly, if you encounter a problem, it will be easier to find if you have only made a small number of changes since the last time you ran it and it worked, and thus you will only have to look through the new code for problems. If you've spent 5 hours coding and hadn't run it during that time period, it's going to be likely that at some point during that 5-hour code sesh you messed up, and it's going to be even harder to figure out where you went wrong. Errors, while annoying and extremely frustrating, are a fundamental part of making you a better programmer.
Alright, now that we've covered errors for a bit, let's hop back onto the programming statement train and talk about one of the most important concepts in computer science, the function. Now you may not know it, but we've actually been talking about a few functions this entire series. Print statements, for loops, and even the basic math operations we've talked about are all examples of functions, which of course begs the question of what actually defines a function. Well, a function is a segment of code that can be easily run by calling the function name, and depending on the type of function, will do something in return. Functions can be called numerous times and in numerous places in your code. Essentially, they are like wrapping up a segment of code into a nice present and giving it a name, which, when called, will unwrap the present and go through the code that you had wrapped up. For example, the print statements we have been using this series allow us to print something to the console anytime we want. Those are functions. You see, we just call the print function and enter in what we want to be printed to the console into the parentheses, and the computer does it for us. Behind the scenes, there is actually even more complex code that is in charge of taking your text and translating it to the console to be printed. The developers of almost all programming languages realize that you don't want to program something that manually has to print something to the console through the use of complex programming, and so they implemented the print statement to reduce the stress and complexity of code on the user, abstracting it to the single line of code that is print. All of that code that is used to print something to the console is wrapped up like a present and given to us in the form of one line. This is actually the main theme of all functions and the backbone of any good program. Oftentimes in your program, there are going to be sections of code which are repeated and serve the same purpose, or equations which you want to allow differing inputs of. And so you can use functions in order to condense these down into singular lines of code to save both time and reduce clutter on your code. As you will see soon, functions are extremely powerful and will definitely be something you utilize all the time in your computer science journey. The print statement is just one example of functions in everyday code. There are thousands of functions that are available to you through the IDEs. However, because we won't always use all the functions that are available to you in a single program, you have to import these functions from packages found in the IDE, which is something that we'll be covering later on. Now there are 4 main types of functions in most programming languages, and they are separated by 2 defining features, whether or not they take in arguments and whether or not they return values. Let's start by separating them by whether or not they take arguments, but first we have to cover what arguments actually are. Arguments are essentially variables that we pass into the function in order to be manipulated and then either returned back to us, printed to the console, or used in another operation. Think of functions with arguments like this. If you walked up to your local Five Guys and told them that you wanted to get food without supplying a type of food, they would probably look at you confused. In order to get the food that you want, you need to tell them exactly what you want to order so that they can give it to you. In this case, getting food is the function, and what you order in terms of food is being passed in as the argument. Based on what you tell them, or the argument that you pass into the getFood function, they will do something different. You should also note that the argument can be many different things. It could be fries, burgers, sodas, really anything on the menu, and such is the case with arguments in programming. Arguments can be strings, integers, arrays, pretty much anything. As an example of a function that takes in arguments, let's look at the max function, which takes in 2 integers as arguments and returns the maximum number between the 2. Now for this function, if you don't input 2 numbers or variables for it to compare, it's going to throw you an error, just like the Five Guys employee. He doesn't know what you want to eat since you didn't provide him with any arguments, and the computer doesn't know which 2 numbers you wanted to compare and return since you didn't provide it with 2 integers. Arguments are a way for programmers to have one function that can do many different things depending on whichever variables can be passed through. Arguments add variability to programming and can help diversify your code. Think of it like this. A restaurant that only allows one type of food to be made, regardless of what you order, isn't going to be very useful or diversified. But if we're able to pass in arguments and tell them which food we want, our experience can be heightened and more options can become available to us, which is exactly what happens when you start using arguments in your function. Now that we've talked about functions that take in arguments, let's move on to functions which do not, because functions can also be created and used without taking arguments in, and still be incredibly useful to the programmer. For example, let's say you are making a text-based RPG game, and one of the options you give your player is the ability to view their stats at various points throughout the game. Now every time you come upon this option, and they choose the View Stats button, you don't have to type out 6 different print statements for every statistic they may have. Your code would get cluttered and messy very quickly. Instead, what you could do is you could package the 6 different print statements in a simple function called print_stats. You don't need to pass in any arguments into the function, since the function will do the same thing no matter what the statistics on the player are. Now, every time the user wants to view their stats, you could simply call the print_stats function, and voila, the user's stats are printed for them to view. This allows you to save a lot of time writing code, but also a lot of space, which is extremely important when your programs begin getting into hundreds and thousands of lines of code and you want to easily search through it to maybe debug. Okay, now that we've separated functions into those that take arguments and those that do not, let's again split these up into those that return values and those that do not. Now the thing you have to understand is that when you're making your own functions, which is something that we'll be covering very soon, you have to choose what your function will return, if anything at all. Functions are able to return values back to the user, whether they be in the form of string variables, integer variables, or even arrays. Now the thing to note about returning variables is that calling the function alone won't do anything. You have to return the value into something or print it out. As an example, the max function we talked about previously would return an integer back to the user, but in order to do something with it, we would have to either set a new integer variable equal to the result of that max function, or we can print out the result of the function, which in this case would just print out the maximum value between the two integers. Using functions which return values don't do much on their own. You have to pair it with something in order to gain the use from it. Let's do another example. Let's say you had created a function which took in 2 string variables as arguments and combined that using that fancy string math we talked about earlier, and then returned them as a singular string. This combined string function could then be used to create new string variables, since what it returns is basically a string. The variable would simply be set to whatever is returned from this combined string function. The last type of function is one that does not return anything, and these are known as void functions. Oftentimes, these are like the print_stat functions that we created earlier, simply used to condense large amounts of print statements that appear often in your code. These cannot be set to variables, since they don't return anything, and just get the code that's within them run through. So there you have it, the 4 types of functions: ones that take in arguments and return something, ones that take in arguments and don't return something, ones that don't take in arguments but still return values, and ones that take in arguments and don't return anything. Each of these 4 types of functions are useful and unique in their own way, and you will probably find yourself using each of them through your programming journey. So get used to the different types of functions, and know how to make the most of them, as they are all extremely powerful. Finally, I'd like to talk about one of the major benefits of functions, which is that it makes it super useful to make large changes to your code without having to go through the entire program. Each function call is essentially just a copy of that function's original code, and so it's very easy to make changes to that initial function and have it translate across your entire code. Let's go back to our print_stats function and say that you wanted to go back and add in a new statistic that the player could level up and through experience in the game. Without functions, you would have to go back into your code and find every instance that you'd printed out the user's stats and create another print statement to display the new statistic. However, if you had created a print_stats function like we did just a while ago, all you would need to do is find out where you define that function and add in a print statement which displays the new statistic, and you're done. Now, every place which you had previously called the print_stats function will now also print the new statistic as well. You can see just how powerful functions can be if used properly, and we haven't even scratched the surface yet.
Now, up next we're going to cover how we can import other people's functions that they've written and use them in our code. Now before we get technical, close your eyes and imagine you are trying to build a house. Sure, you could grow your own trees, chop down your own wood, make your own tools and nails, and build it from scratch. But why do that, when you can simply go to your local Home Depot and buy these materials that others have already made ready for you? That's the main idea behind importing functions into your code. Importing functions allows you to gain access to libraries of functions that other people have already made for you. This is just as useful as it sounds. There are so many functions that are super useful for any given program that it would take you forever to write them all yourself. Luckily, other people have already done most of this for you. In each programming language, you are able to use an import statement to import libraries of functions into your program that you can use as you write it. A library is simply a collection of functions that all have the same theme. It may be a math library, a data analysis library, a library which translates text, or anything you can think of, really. There's such a variety of libraries for any given language that most functions you require that are not hyper-specific to your program can likely be found in some library. In fact, a good portion of any programmer's job is looking online for packages which can make his or her job easier instead of handwriting functions. Now I can hear you saying, "Wow, that's sick! How do I do it?" Well, it's quite simple. An import statement. In most languages, an import statement consists of three parts: the library you would like to import from, the package you would like to import from that library, and then which class from that package you would like to use. For example, we could load up the Java library, and from there import the util package, short for utilities, and then from that utilities package, import the scanner class, a class which allows us to read information from the user. A package is simply a smaller set of functions and methods to help differentiate between the thousands of methods contained in a library, and a class is even more specialized than that. Now, if you don't know what specific classes you're going to want to pull methods from, you can use a star to import all classes within the package you'd like. However, it can be beneficial to be more specific and only import the classes you would like, as it helps with the efficiency of the program in the long run. For instance, in Python, the syntax to import a library is import followed by the library name. However, importing an entire library is more computationally taxing than importing specific functions from a library. Imagine you would only be using the factorial function from the Python math library. It would be a waste of computing power to import the entire library, and it would increase the load time for your program. For smaller programs, this isn't a big deal, but it really starts to add up when dealing with larger projects. Therefore, you would instead use from math import factorial, or the Java equivalent import java.math.factorial, and now have access to that one math command only. This limits the functions that you can use. However, it saves programming runtime. If you decide you want to use another function that you hadn't planned for, you can always go back and import that too. Many times, if you try to use a function from a common package and you have not yet imported it, the IDE will prompt you to do so. If you're trying to figure out which libraries you want to import, think of the functions you're going to need in your program. Perform a simple Google search, and you will probably run into a package or library that already exists in your IDE that you can use. And if you can't, there are ways to download and import additional projects to fit your needs. But what if, after all that, you still can't find a library that contains the function you're looking for? Well, that's a perfect segue into what we're going to talk about next, which is the basic structure for writing your own functions.
So at this point, we've talked about both what functions are and how we can get some very useful functions by importing them through packages. But there are definitely going to be moments in your programming career where you're going to want to make your own functions because you want one to be made specifically to your program and code. Luckily, making your own functions is extremely simple. There are just some basic rules that I want to cover. Now, while we've previously used making functions as an example for other topics, such as the player stats function from a little bit ago, they were extremely abstract and didn't go into depth into what is needed for an actual function to operate. So right now we're going to be covering a skeletal system of everything that needs to be included in a function in order to get it to work. Now think back to the 4 different types of functions that we talked about previously. Functions that do and don't return values, and functions that both do and don't take in arguments. For creating your own functions, we're just going to have to go down the list and talk about how to approach creating each one of them, starting with the most basic of the bunch, one which takes in no arguments and returns no values. But before we start that, there are a few small things I want to note about function naming conventions. The variable naming conventions we talked about previously also translate over to function names. So you can't have two-word functions, and you can't use special characters like periods or commas. Generally, you're going to want to follow the same camel case style which we talked about in the variables video, which is not capitalizing the first word, but capitalizing each word after that. Alright, so in general for making functions, each language differentiates on how you tell the computer that it's actually a function. In Java, you have to define the function scope, which is something you don't really need to know unless you're going to become more invested in Java, but basically it tells the computer which parts of the code can use the function and which type can't. For this series, all of our functions that we make are going to be public. From there, you then determine which type of function it is. So in this case, since it won't be returning any variables, we'll just put void to signify this type of function will not be returning anything. Finally, you put the function name after those two identifiers, along with a set of parentheses after it like so. The parentheses are where your arguments would go if you were making a function that took in arguments, but since for our first type of function we're not incorporating arguments into this function, let's just leave those blank. All of that is just for Java. Python, on the other hand, all you have to do is put the word def, short for define, and then the function name with a set of parentheses. So as you can see, each language is going to be a little bit different in how you make functions, but the main thing we want to remember is to always add parentheses. From there, we just type what we want our void function to do within the confines of the function and close it off, and we're done. In Java, the confines of the loop would be whatever is contained within the curly braces, and in Python it would be until you are no longer indented. At its core, this is the most primitive type of function we've made, something which takes in no arguments and returns no values, quite similar to the print_stats function from early on. Moving on to the next type of function, creating a void function that takes in arguments. Now this process is going to seem very similar to the previous, except for one small adjustment. Remember the parentheses that I mentioned earlier? Well, we put any variables we want the user to pass into the function into these parentheses, and then when we call that specific function, it will be required to have those variables passed into it. For example, in Java, let's make a function that takes in two numbers and prints out the product of those numbers. We start with the public void plus name of function setup again, since we won't be returning any values. And here comes a new part. Inside the parentheses, you define which type of variables you would like to pass in as arguments. In this case, an integer, and then a name for that variable. This name is what you will use to refer to the integer that the user passes in. For example, let's just call it num1. Then, if we want to add another argument, we simply add a comma in between the two, and we can make another integer variable, num2, to hold the second number. We could do this for however many variables we want to pass into the function. But for now, let's close off the parentheses and just print out the product of num1 and num2. As you can see, we refer to the two numbers that the user will input into the function as num1 and num2. Whatever numbers that the user passes into the function will be converted into num1 and num2. Now, whenever we want to call the multiply numbers function, we just have to make sure that we are putting two numbers in as arguments. In this case, the number 5 becomes num1 and the number 8 becomes num2. From there, we simply run the code and the number 40 is printed to the console. It's pretty important to note that you can also mix and match variables when making arguments. So you can have some function which takes in a car, an integer, and two strings all within one function. The last thing I want to mention about arguments is that when you call a function, you have to follow the variables you defined when making the function. So for our multiply numbers function, you couldn't put in a string and then an int. It has to be two integers because that's what the computer is expecting to be passed into the function. So now that we've gone over how to make functions that don't return variables, we have to cover those that do. And we'll start with ones that don't take in arguments. Now the main difference between defining functions that return variables and defining ones that do not is that in some cases you have to specify that you want this function to return an integer variable. This is most common in Java, where you would replace void with int to tell the computer that you want this function to give you something back to you in the form of an integer. This works the same as if you wanted to return a string, char, or even an array. You simply replace the word after public with whatever variable you want to be returned by that function. The most important thing to remember about making functions that return variables is that no matter what path your code takes, it must return a variable, no matter what. What does this mean? Well, let's say you had some string function in a game, and inside of it there was an if statement, where if the player's score was above 10, you returned a congratulatory message. This works fine if you printed the result of this function and the player's score is above 10, but if the player's score was less than 10, then you don't enter the if statement, and then you don't have something prepared to be returned to the user, and so the function is going to throw you an error. You have to have all your paths covered, which may seem simple, but if you're making a function with a switch statement in it containing high amounts of cases, then this can get out of hand very quickly. Something I like to do to make sure this doesn't happen is put a return statement at the bottom of a function with a string or an integer so unique that I'm able to tell that the code is not running properly and can fix it. Also, usually an IDE will let you know if there is a path in your code or in a function that does not return a variable when it should. The main point I'm trying to get across, however, is always cover your exits and make sure you have a return statement prepared for any case the user may throw at you. Another small thing to note is that you can't return one type of variable if you've already defined the function to return another type. For example, you can't return a string in an integer function or vice versa. The return statement must always match the type of function, no matter what. The final type of function is one that returns variables and also takes in arguments. And for these, all you need to do is combine what we've learned from the previous cases. First, you assign your arguments in between the parentheses, making sure that you have also defined what type of variable you want to return, and then ensure that no matter what path the code takes, that you're always returning that variable type. That concludes our discussion on functions. As you can probably tell, functions are an extremely vast subject area and require a little bit of practice to fully understand, which is why later on in this series we'll recommend some websites you can use to practice those more difficult topics.
Now, I'd like to switch gears a little bit and continue our discussion from earlier on arrays. Arrays, while useful, aren't the only way to store and manipulate information. In fact, there are a multitude of different ways to store data in computer science, including linked lists, stacks, queues, maps, trees, and many others too. Right now, though, I'd like to talk about two cool, wacky, and zany ways to store data that we haven't previously covered: array lists and dictionaries. But before we get into those, let's get a little review and reinforcement of arrays. As you may remember, arrays are basically lists of values that are stored together. When you initialize an array, you give it a size, and this size is fixed. You won't be able to increase the size of the array, so when you make an array, its length is final. To access the values in an array, you reference them using an index which starts at 0. What this means is that the first item of an array is not at position 1, it is at position 0, and its position is commonly referred to as its index location. So, to find the nth item in an array, you would refer to it as index location n-1. However, as the size of an array is fixed, you have to be careful to not reference a position that is beyond the total size of the array, or to append too many items to it, as this will return an error. We also have what are known as two-dimensional arrays, which is an array containing an array at each of its indexes. Or you could have an array containing arrays, containing arrays, containing arrays, containing arrays, depending on what you're trying to do. Multidimensional arrays can be useful in more advanced programs for organizing a wide volume of related values. If that's confusing at all, skip back to earlier for our full discussion on arrays. The timestamp will be in the description. Now that we've reviewed arrays, let's go over array lists. Array lists, or just lists in Python, can be thought of as a growing array. Earlier, we mentioned how you have to be careful to set an appropriate size of your array and to make sure that you only reference and append values such that you remain within the size. However, with array lists, this isn't a problem. After you initialize an array list, it instinctively has a size of 10. But if you append values such that the size of the array list goes beyond 10 elements, an array list will grow itself, meaning that the computer will allocate more memory to the array to increase its total size so that the new values can be appended. This is quite useful when you don't know the exact number of values that the array will need to store, or you want the ability to store more values to your heart's content, such as when you're making a database with an unknown amount of users that will sign up. There is a lot more to uncover when regarding array lists, but for this surface level series, that is all you pretty much need to know. So let's move on to dictionaries. Now when we're talking about dictionaries, we're not referencing that thick book you probably have lying around your house, which has thousands of definitions. In computer science, dictionaries are like arrays in that they store multiple values. However, their values are stored very differently. Rather than being referenced by their linear position within the dictionary, each value is tied to another value that is used to reference it, or its key. Because of this, we need to throw away all conceptions of dictionaries as a linear way of looking at data, since in actuality, it is much more fluid and interchanging. Basically, we say that each position in a dictionary holds a key-value pair. When referencing a value in a dictionary, you will use its unique key, and the dictionary will tell you the value that it is tied to. Think of it like this. Each time you add an item to your dictionary, your computer creates a handcrafted box to store the data, and also custom makes a jewel key, one of a kind, no other like it in the world. This way, there is only one key that goes to the box that stores a certain bit of information. Because each key must be unique, reusing the key in a dictionary will result in an error being thrown, because having two keys that are exactly the same would confuse the computer as to what box, or piece of information, that key leads to. However, you can store the same value in multiple key value pairs, since the keys would all be different. Now, like I said, dictionaries are more fluid, making them easier to organize than arrays, as everything is set up in a more logical manner. That is to say, it is easier to find the value you are looking for when you are using keys rather than simply referencing their positions. Let me explain what I mean. Imagine you have a dictionary of prices at a store where the key is the name of the product and the value is the price of the item. Maybe apples cost $1, milk costs $2, and bread costs $3. You can see that in the dictionary, each key is the name of a product, and each value corresponds to the price of each product. So to find the price of bread, all you need to do is simply call the dictionary using the key bread. This makes it extremely easy to track values through your code, since you're working with tangible values rather than numbers which don't mean anything to you. You can also manipulate dictionaries in many of the same ways you can manipulate arrays and array lists. You can iterate through a dictionary and perform many operations and comparisons on the values. If you want to find the product with the highest price, for example, you can iterate through the dictionary to find the value that is highest amongst the grocery store items. Arrays, array lists, and dictionaries are useful in their own right, as are the mass amounts of other ways to store data, and each boast certain advantages over one another. We already covered the basics of these three, but since there are so many, we don't have time to go in depth into each and every one of them. And so in order to help you grasp the basics of storing information, we're now going to talk about one of the most important functions needed to understand arrays, which are searching algorithms.
Now, just as there are many ways to store information in computer science, there are even more ways of searching through lists. Searching algorithms, at their core, are ways in which we can look through a list of values stored in an array, say a patient name list or a high score list, and find a particular piece of data. The goal of a searching algorithm is simply to give the algorithm a string or object you want it to find, and have it return the index of the array that contains that string or object as fast as possible. Now, while this may seem simple, lots of software runs on the backbone of being able to search through lists extremely quickly, making searching algorithms, and in particular efficient searching algorithms, an important topic to cover. Additionally, this is the main functionality that arrays are used for, and is the backbone of many of the methods used within array lists, as well as many other storage methods, so knowing them will take you a very long way. Typically, searching algorithms are used to return the index of a particular data point so that it can be used, modified, updated, or checked on. For example, if you're about to check into a hospital run on an array system for patients, the staff must search through your name in the database, and by returning the index of where your name is, they now have a quantifiable number that they can use to easily check you in, rent out prescriptions, schedule you for checkups, update your personal information, etc., without having to search through the list for your name every single time. You may think that there's little difference between searching algorithms, since computers nowadays can perform millions of calculations per second. But when you're a huge multi-billion-dollar corporation trying to find a certain data point in a list containing thousands or even millions of data points, small differences in efficiency are going to make or break the user experience. Even a 1% improvement in efficiency can mean big differences in the amount of time that a user is waiting for a simple task. Now, before we jump into different types of searching algorithms, we must discern between the two states that arrays or lists can be in, either sorted or unsorted. A sorted list of information is characterized by some sort of rankable value, whether that be a patient ID, credit card number, or even by alphabetical values like usernames or legal names. An unsorted list is just some random assortment of related information not sorted by any particular order or reason. Some searching algorithms only work for sorted lists, usually the more efficient ones, and some work for both sorted and unsorted lists. Although these are usually less efficient, if you end up pursuing computer science further, you'll have to deal with both sorted and unsorted lists, so it's good to know a common searching practice for both. Another thing to note is that we determine the efficiency of searching algorithms based on both the worst case scenario and the average number of items it must search in order to find the index. We call this Big O notation, in which each searching algorithm has an equation which takes in the size of the array as an integer n and will output a worst case scenario efficiency value that we can use to compare with other searching algorithms. We can then also look at how long, on average, it takes to find an element in a list. Using these two methods allows us to easily compare how efficient two algorithms are. Alright, now that we've got some background on searching algorithms, let's hop right into it. The first type of search we'll be talking about is called a linear search, and you've honestly probably used this multiple times throughout your life. Every time you have to search for your name on a list of people, you probably follow the same pattern. You start at the top, check to see if the first name on the list is yours. If it is, great. If not, you move on to the next name on the list until either you find your name or you don't, in which case you leave. A linear search works in the same way. You start with the first element in the list, compare it to the value that you're trying to find, and if they're the same, you found your match and you return the index of that element. And if not, you move on to the next element in the list until you either find the thing you're searching for or you run out of lists to check. Pretty simple, right? This is because linear searches are pretty bad when it comes to efficiency, especially in the worst case scenario. If the item you're searching for in the list is the last element, you're going to have to check the entire list of items before you find the one you're searching for. On average, however, you're going to get it about halfway through the list. This makes the linear search O of n worst case scenario, since in the worst possible case it will take the entire length of the array, or n, to find the correct value. The linear search on average will return the correct index in O of n divided by 2, or halfway through the list. Now, while the linear search isn't great, it can work with both sorted and unsorted lists, because of the fact that it will eventually cover every element in the list. The other search we're going to cover requires the list to be sorted, which may seem like a drawback, but having a sorted list allows you to use algorithms that are far more efficient than the linear search. So overall, the linear search is a good basic searching algorithm for if you have an unsorted list, but if your list is sorted, there are way more efficient options out there for you, such as the binary search, which we'll be talking about now. The binary search uses a recursive process to break the data in your list down into more and more manageable bytes, taking advantage of the fact that it's sorted in order to find the item you're looking for faster. This one is much harder to wrap your head around, so let's start with an example. Let's say you have a list of 10 names sorted alphabetically, like shown on the screen now, and you wanted to find your name within that list. In binary search, you would look for the middlemost name, in this case the one at the 4th index. Just a quick aside, since there's no true middle, since the list is 10 names long, the computer automatically uses the next one down as the middle value. Now, once you find your middle value, you first check to see if the name you're searching for at the index you've chosen is the name that you're looking for. If it is, you simply return that index. But 99% of the time, it's not going to be, including right now, so let's keep going. If the value at the middle name is not equal to the one you're searching for, you check to see if the value you're searching for comes before or after the middle index. For example, if you were looking for the name Brendan, and the value at the middle index was Carl, Brendan obviously comes before Carl alphabetically, and since we know that the list is sorted, what we can now do is ignore the entire bottom half of the list and just focus on the top, since we know that if Brendan is even in the list, it's going to be in that top half. Now, we simply treat the top half of the list as an entirely new entity and repeat the process over again. Again, we would find the middlemost element of this new list of names and again compare it to the name you're trying to find. If it's the name we're trying to find, we return that index. But if not, we compare it to see if it comes before or after the middle index. Going back to our example, let's say the middle index of this new list is AJ. Now we know that Brendan comes after AJ alphabetically, so what we can now do is ignore the top half of the list, since we know that if Brendan is in the list, it's not going to be in the top half of our list. Now, we again repeat this process again and again until we find the name we are looking for. So for our example, the middle index this time is Brendan, and that's what we're searching for, so finally we would return the index 2. In binary search, eventually the index we would compare to our search term will be the same, and once it is, we can return the index and move on. Now if we don't find it, which happens after we have eliminated the entirety of the list without finding our search term, the algorithm will simply return a null value to let you know that the item you're searching for cannot be found in the list. The binary search is way faster and more efficient than the linear search, since we are drastically cutting down the amount of elements we have to look at, making the program run faster. In almost 99.9% of cases in which your list is sorted, the binary search is going to return a result faster than the linear search. So, if you have a sorted list, your best option is to go for binary. As for efficiency, the binary search is O log n for the worst case scenario, which could be confusing if you don't fully understand logarithms, but all you need to know is that it is way more efficient than the linear search. Its average scenario is actually also O log n as well, which again is infinitely times more efficient than the linear cases. Now while there are other types of searching algorithms you can use, these two are the most common for both unsorted and sorted lists, so we will stop there for now. Up next, we're going to be covering one of the most confusing and important topics in computer science, recursion.
Let's start with the most important question. What exactly does recursion mean? In programming, recursion refers to functions that repeatedly call themselves, meaning that in the instructions that occur within a function, one of the instructions will be a call to that same function you're already in. In the extremely primitive example on your screen now, you can see we have some function which, in the confines of itself, calls itself. A recursive function will usually take into account some integer as an argument, and will use this to carry out some instructions, modifying the integer that was entered, before calling itself again with that new integer as its argument. To better understand these functions, let's discuss the basics of how we go about programming one of them. A really good and easy example of a recursive function is one which sums up all numbers from 1 to n. So let's make a recursive function that does just that. The first thing we need is the actual function, and we're going to make it an integer function, which takes an integer n as its argument. The reason we do this will be explained later, but for now let's move on to the base case. A base case is simply a definite value which all recursive statements, the ones that are being repeatedly called as we go through the function, try to get towards. At the beginning of the function, we test a value that was passed in by the argument against the base case to see if it is satisfied. Usually, these base cases are some requirements, like if n, as I described before, reaches a certain value or is equal to a certain value. It is extremely important that the base case is set to some requirement that n will eventually meet for the same reason that it is important to avoid an infinite loop. We do not want a stack overflow error to occur. For example, if our base case was to stop calling the recursive function when n was greater than 100, and if it is not, we will call the same function again but with n minus 1, and we started with n as, say, 99, we would never reach the base case, and the recursive function will repeatedly call itself over and over again, subtracting 1 from n, and hoping that somehow it will eventually be greater than 100, until your computer crashes. Not fun. So anyways, back to our recursive sum example. Let's make our base case when n is less than or equal to 1. This way, we can start at some positive integer n, and subtract from it until it is less than or equal to 1, in which case we can exit the recursive statement. Cool. Now, if n is not less than or equal to 1, what we want to do is return the sum of both n and then the returning value of our recursive sum method minus 1. Why do we add n and the function call? Well, let's actually go through the function as if we were the computer and see why. We start with a call of recursive sum with n equals 3. We know that 3 is not less than or equal to 1, so now we try to return a recursive sum of n, which is 3, and the returning value of recursive sum with an n of 2. We don't know what the returning value of recursive sum with an n of 2 is, so we have to go through the function again, only this time n is 2. Again, n is not less than or equal to 1, and so this function will go through the else statement and return 2 plus another recursive statement, in this case the returning value of recursive sum with an n of 1. So once again, we have to go through the recursive sum function to get that value that will be added to 2, and then returned and added to 3, and then returned. Hang in there, we're close. Now in this function, n is less than or equal to 1, and so we return n, which is 1. Now we take that n, which again is 1, and that is what gets added to 2 in the previous function call, and then returned. So this would return 3. Now this 3 is what gets added to the first function call, which is 3, and so it becomes 3 plus 3, which is 6. And finally, after all that time, we get 6 returned from the function, which, if you've been following along at home, 3 plus 2 plus 1 is, indeed, 6. Now this may seem like a waste of time since 3 plus 2 plus 1 is not a hard operation, but to those of you saying that, I ask you to please give me the sum of all the numbers from 1 to 3,567. Godspeed. Now recursion is a very difficult concept to wrap your head around, so if you're not 100% comfortable with it at the moment, feel free to rewatch this section of the video in order to better familiarize yourself with it. Alright, cool. Now that we have a little background on recursion, let's talk about why it works so well. Now to understand why and how recursion works, we must first understand what a stack is. A stack is a data structure that contains all of the tasks you instruct your program to complete. Based on a certain method, your program will then carry out the tasks you give it. It's called a stack because if we start another process before the previous one completes, the process is stacked on top of the other one, such as the animation on your screen is showing now. Programs we write will follow the LIFO structure. For those unfamiliar with accounting, LIFO means last in, first out, or the last item put on the stack will be the first one removed from it. Essentially, every time you ask your computer to complete a task, that task is added to the stack, and will be the first one to be resolved. Think of it like a stack of stones. You can keep adding stones on top of your pile, but in order to get to the one at the bottom, you must first remove all the rocks on top of it. Now when your function continually calls itself without end, without a base case, like in our infinite loop example, then the stack will never be resolved, as items will be continually added to the stack without any of them ever being completed. In this case, the memory allocated to the stack exceeds the maximum allowed, and a stack overflow error occurs, resulting in your program crashing. Think of this as if you're doing chores, and before you complete one chore, you get called to do another chore, and then before you can complete that one, you get called to do another one. Since you keep stacking tasks, or chores, on top of one another, the stack of tasks will never be completed, and you will probably die before ever finishing all of your chores. This is the same logic that makes infinite loops crash your program. Recursion works on these same principles. The initial call makes a second call, which is added to the stack, and now that one must be taken care of first. But in that one, another function is called, which gets added to the stack, and so on, until you reach the base case in which you slowly start going back down the stack. In conclusion, recursion in general is extremely useful because by calling the same functions repeatedly, it breaks down the problem into smaller sections and results in the program being more efficient. Small parts of problems are easier to solve and less taxing to compute than the entire problem at once, and the computer can combine these small solutions into the whole solution at the end.
Now, as we wind down our Introduction to Programming series, we want to take some time and go over some of the soft skills needed to be a successful computer scientist, since it's not all about writing code. In fact, many professional computer scientists will tell you that the majority of their job is spent thinking about code, rather than actually writing it. This is because much of programming boils down to problem solving. How do we optimize this system? How can we make this feature for our app? What type of movement do we want for our game, and how can we program it? The harsh truth is that no good program has ever been written simply from the programmer getting the prompt or idea, sitting down, hopping on an IDE, and starting to write code. There are many tasks we should go through beforehand in order to plan out our code, so we ensure that when the time comes to program, it's a clean and easy process and not riddled with mistakes and bugs. This is where pseudocode comes into play. Think of pseudocode like this. If you wanted to take a family trip to the Grand Canyon, would you simply hop in your car and drive off and figure out things later? No, because that would be ridiculous. Instead, you would spend some time planning out the trip. What sites or places do you want to visit? What hotel reservations are you going to have to make? What kinds of things are you going to do when you get there? What routes or highways are you going to take and why? All of these things must be determined before you can even think about hopping in your Ford Explorer. So how does this translate to pseudocode? Well, think of our family trip to the Grand Canyon as a program. Programmers use pseudocode, pseudo meaning not real, and code meaning code, as a means to plan out their programs before they write them, just like how we planned out our trip before going. They throw away syntax and naming conventions for variables and just focus on what they want the program to accomplish and how they plan on doing that. Pseudocode is very similar to constructing an outline for a paper that you're writing. You write down the main topics of the essay and plan out your major talking points, but you don't worry about the nitty-gritty details of it all, such as word choice, grammar conventions, and proper formatting. By doing this, we allow ourselves to think freely and not worry about stressing the small stuff, at least not yet. Alright, now that we know what pseudocode is, let's talk about how we write pseudocode. You see, the best part about pseudocode is that it can take the form of many different things for many different people. Each computer scientist has their own methodology for planning out their code, and there are probably hundreds of different methods of writing pseudocode that are out there today. Today, however, I'd like to focus on 3 popular ones that I think you might find to be extremely useful. The first of these is known as flowcharts, and mainly they can be used to think through the process of a particular function. A flowchart is fundamentally a graphical representation of a function and how it might flow. Many programmers do this and lay out the conditional statements and loops that they want as different blocks in the flowchart, connected by arrows and charting out every path of their function. From there, it's extremely easy to create test cases and follow them through the flow of the function through the different blocks and arrows. For example, we could have a flowchart that goes something like this. A user enters in a number, and if the number is 8, I want the program to return true. However, if the number is not 8, then I want it to return false. It's a great way to visualize what the function's overall purpose is, and also look for any errors that you may have missed when thinking about the function, such as a missing path. It also abstracts the programming statements up to simple blocks, making it easier to modify or change completely. The best part is that when you have finished testing cases, you can simply convert the blocks into programming statements and you have a well-written function without any debugging. Another popular pseudocode technique that is often used is to simply write out what you want your code to do chronologically. Don't necessarily think about what programming statements and functions you want to use, just jot down, from start to finish, what it is the program you're writing is going to do step by step. For example, let's say you're making an app that takes in 2 numbers and divides them. The pseudocode for that would look a little something like this. First, I want to prompt the user to enter a number, and then I want to wait for the user to enter in that first number. After I get the first number, I want to again prompt the user to input a second number. Once they do, I complete the operation by dividing the 2 numbers entered and returning the result back to the user. This all seems like it would be common sense, but remember that oftentimes we're not going to be working with simple multiplication or division functions. We may be working with full-scale games, algorithms, or user interfaces with many different options. This method allows you, the programmer, to not get bogged down with the syntax and conventions that you have to follow. You're simply making a note of what the program's ultimate goal should be, as if you were explaining it to a friend of yours. This method really lets you plan out everything that needs to happen in your program in order for it to run smoothly. It also ensures you don't forget about a piece of an algorithm or a certain function that you need to write in afterwards. And the final pseudocode strategy that I'd like to talk about to you today is writing out the main features you want the user to have when using your program, and what functions or smaller programs you're going to need to complete these features. Let's do another example. Say you're making a banking interface, and on startup, you want the user to initially have 2 options. They can set up a new account or log into an existing account. From there, if they log into their account, then you want them to have the functionality to withdraw money, deposit money, take out a loan, or pay back a loan. If they decide to set up a new account, you want them to be able to create an account, store their information in a database, and then access all of the features that a returning member would have. This may look very similar to the flowchart method, the only difference being that this is abstracted one level higher over an entire program rather than just a single function. If you really wanted to, you could also create a flowchart that would go through the functionality of all the 4 methods described above. Setting up a hierarchy, like seen on your screen now, makes it easy and clear to see every function and interface you're going to have to make. This prevents you from having to try to shoehorn a function or feature into an already finished program at the last second, which is not a very fun experience in the slightest. So there you have it, 3 pseudocode strategies you can use to plan out your code before you even start writing any. The flowchart method, which is good for thinking through the flow of a certain function, the write-up method, which is good for getting the general idea down for a program, or the functionality planning method, good for listing out the functions of a certain program. You can use all of them, none of them, a mixture of them, or even disregard these and find and create your own pseudocode methods. The main goal here is to drastically minimize the amount of errors that occur during your program and relieve a lot of stress on your head. The importance of pseudocode cannot be stressed enough, and if you don't believe me, I urge you to try to complete a large project without it.
Okay, so if you've watched the series up until this point, you've gotten a pretty good understanding of many aspects of programming, and also how to plan out your programs. Now it's time to go out into the real world and write some actual code. But what kind of program? I can hear you asking me. And the answer is truly whatever you want, really. As I'm sure you know by now, you can program just about anything you have on your mind. Anything from simple games to complex software. This video has equipped you with the basics that are going to need to be used in pretty much any program you decide to write. But that doesn't mean that every programming language is perfect for every application. Each language has its own strengths and weaknesses, and choosing the right one is very important for making it easier, and sometimes just even possible, for you to program what you want. So that's what we are going to be talking about now, choosing the best language for what you want to accomplish. Now, we talked earlier about low-level versus high-level programming languages. In case you forgot, let's do a quick refresher. Higher-level programming languages have a higher level of abstraction from machine language, that series of zeros and ones from way back when, while lower-level programming languages have a low level of abstraction from machine language. For example, block programming, where you can drag and drop programming statements together like 2D Legos, would be a high-level language, as it does not take a high level of understanding of the inner workings of a computer to program it. The theoretical highest level of a programming language would be if I could just write down what I wanted the computer to do in simple English and it would just work. But, sadly, that doesn't exist yet. On the other side of the spectrum, the lowest level programming language would be just feeding zeros and ones into the computer at supersonic speed, which would be almost impossible and extremely absurd. So, how do you choose what type of language is best for your needs? Well, it depends on what you are trying to do, as sometimes you need very specialized languages to get done what you want. The world of computer science is vast and contains many fields, so trying to cover everything in one language would be impossible. This has led to the creation of hundreds of different programming languages, each designed for a specific task. Right now, though, we'll cover some of the most popular languages and their uses. Now, if you are trying to design a website, using HTML and CSS is probably your best bet. HTML is a markup language that is designed for writing the content of a website, while CSS is great for designing the style of the website. You interact with HTML every day, and you can even see it right now if you right-click and hit Inspect Element. This will truly show you how complex HTML and CSS can be. Maybe it would be best for you to use a scripting language. A scripting language is a language that has many commands for you to use, and that can also be run without needing to be compiled. Scripts can be faster to write than most programs, and tend to be easier to port between operating systems, allowing for cross-platform support. Scripts can also be used with websites, oftentimes adding to the overall user experience of the site. If you want to go into web design, this might also be a path for you to go down. Examples of scripting languages are Perl, PHP, Ajax, and JavaScript. For most programs, you could probably use a general-purpose language. General-purpose languages, as they sound, have a wide range of applications. Usually, these should be your go-to languages. Examples of general-purpose languages are Java, C++, and Python. They each have their own different benefits over one another. Java is very useful for developing games and interactive web pages. Python can act as a scripting language for web programming as well as writing applications and data analysis. And C++ tends to be used for writing applications and system programs. They all have a variety of packages that you can import and use to achieve the functionality you need from them. While selecting the right general-purpose language for your big projects is very important, for most of your programs, any one of them will work. It really comes down to preference. Get to know each language and decide which one's syntax rules you like best and find most comfortable. If you get to know one general-purpose language really well and enjoy programming with it, you can apply it to just about any of the programs you plan on writing. Personally, I tend to use Python for most of my projects. This is mostly not due to any functional difference between Python and any other general-purpose language, though there are a few, but it is mainly because I find its syntax rules most convenient and easiest to write programs with. Overall, either you can consider the project you plan on doing and research and see which language boasts the most advantages for your purposes, or you can simply become comfortable with a language and use it for most of the programs you decide to write.
We'll now be looking at our final topic of this Introduction to Programming mini-series. You now have the basic knowledge of programming, which will take you far in any language that you decide to learn. You know some good pre-programming pseudocode strategies to help you design your code from the ground up, and you might already have a good idea as to the type of programming language you might want to start with. So what's the next step? How can I learn that language, and what applications can it be used for? Well, that's what we're going to be covering now, so let's just jump right into it. Starting with the biggest question, which is what is the next step? Well, now that you might know which type of language you might be interested in, research that language and find out whether or not you truly want to pursue that programming language. Most languages, like Python or C++, will have either an official website where you can read up on the language, or a Wikipedia page which will provide you with useful information in deciding whether or not you want to pursue that path. From there, the next step is to actually learn the language, which can be done right here on YouTube. While we have taught you the basics of any programming language, each specific language is going to expand upon these concepts, and so watching tutorial videos on a certain language is going to be very beneficial. I would start with an introduction series, like the one you're currently watching, but for the language you have chosen, and work your way through that series, picking up on the syntax and rules of that language until you become comfortable with it. Once you do that, you come to a crossroads. You know how to program in a certain language, but you may be completely clueless as to what to make in that language. Programmer's block can leave you uninspired and not want to continue programming, so I'd like to give you a few websites to help out. First is CodingBat, a completely free website which has hundreds of coding challenges in both Java and Python to help you refine your programming skills and even learn some new programming shortcuts and tips. This is great if you want to get better at improving your efficiency and need something to hone your skills as a developer. The next is CoderByte, which offers over 200 plus challenges that you can complete in over 10 different languages, something that is sure to help you improve. The final website I'd like to talk about is HackerRank, which not only provides programming challenges to keep you on your toes, but also provides support for you using your programming skills to find jobs or internships. These and many more websites exist solely to keep you interested in code and work on refining your skills to become better. Now, if you're a teenager watching this series in high school, I also encourage you to take programming classes in your high school. AP Computer Science Principles and AP Computer Science A are both amazing courses which can help you greatly in the future, and are also incredibly informative and important to colleges. Your school might also offer other classes in the field of computer science, including ones on data structures, game design, and data science. Any and all classes you can take to help expand your knowledge of programming and help you find your niche is going to be extremely helpful. As you can see, the world of code has now been opened up to you. These are just a few examples of where you can go from here, but there are many more we didn't talk about. You could get into GitHub and start contributing to projects. You could work on your own projects and collaborate with others. The possibilities are endless. The next step is up to you. This concludes our Introduction to Programming mini-series. We hope you enjoyed watching it as much as we enjoyed making it. If you enjoyed the series as a whole, consider subscribing to our channel, Null Pointer Exception, which will be linked in the description, for more content like this coming soon. Thank you so much for watching.